test. Okay, less than 2 seconds. So, all can hear, right? Good afternoon. So today we will cover the dynamic programming in this 1 hour lecture. Before I start this lecture, I think I need to clarify one thing. I think this statement is there's some confusion. Someone asking, if the graph is strongly connected, the 3T constructed by the DFS depth first search algorithm is a spanning tree. Okay, a set of V minus 1 edges that connect all vertex. Yeah, because it's strongly connected. So all vertex of the graph will form a depth first search spanning tree. Okay, so this statement is correct, but doesn't mean that given you a graph, you able to start from some point, maybe like this case A, in this example A, you start from A, you can form a spanning, that you apply the depth first search, you get the depth first search spanning tree. Doesn't mean that this particular graph is a strongly connected graph. Okay, this is the logic problem. If the graph is strongly connected, you can form the spanning tree. But doesn't mean any graph form a spanning tree implies that graph is a strongly connected. Because to form the graph is strongly connected, that means any vertex can find a path to any vertex. Yeah. So well, that is something in the tech notes. So someone asking that how is it because this particular example, actually maybe I choose the not a good example, or maybe it's a good opportunity for you to know that this particular graph is not a strongly connected graph, as I mentioned. Very clear, because this guy, you cannot see, you start from C, you cannot go to any places. So this one actually is not a strongly graph. But if I start from A, I'm still able to form the spanning tree. Even in fact, you can start from any vertex. You can form the depth first search spanning tree, but this depth first search spanning tree may not connect all the vertex of the graph. May not. Okay, so maybe this I need to clarify. The rest, I think, this one Monday already discuss about it. So anything I need to say? Okay, for I think quite a few trying to ask about assignment. For assignment 7 and 8, the last assignment, in short, the last assignment, you only the last question I allowed you to not to use my template. Actually, I'm trying to, originally I plan is like not even give you the template for the last question to at least you show that in the end you're really able to write the whole program by your own from sketch. From given you a problem, you're able to come out the algorithm, then you're able to write a program to solve the problem. That is the things. But I think maybe I in the end I still give it some of you. I'm worried that you may not be able to do that, some of you, but I can see some people already can do that. Well, that's good. Can briefly explain how to utilize the array list in the assignment 7. Which one you refer to? Which question you refer to? Assignment. Where's my assignment? Where's my assignment? May I know which question you're asking? Question 1, question 2, question 3, question 4. Okay, I guess it's question 3. Next. Okay, I answer few first before I start the lecture. Then the assignment list is the I guess it's question 3. Question 3, maybe. What is the question? Oh, yeah. Here. So you asking array list. So you need to, okay, this one, yeah, you need to, yeah, it should be an array. It should be an array to show all the possible, sum to C. So let's set my C. I guess you're trying to ask if my C equal to 6, then a possible answer is 1, 2, 3. 1, 2, 3. 1, 1, 2, 3, 1, 2, 1, 2, 3, 1, 2 cannot. 1, 3, 1, 3, 1, 3 cannot. 1, 3, 1, 4, 1, 5. I think next one will be 1, 5. Will be equal to 6. 6 is 1 equal to 6. 2 plus 4. Okay, I miss out 2 plus 4. And then 1 plus 1, 2, 3. 1, 2, 3, 1, 3. 1, 4, 1, 5. 1, 5. Then 1, 6 cannot. 2 plus 2 plus 2 plus 4. 3 plus no more 4 plus no 6 no. So the last one is 6. 5 no more 6. I think 1, 2, 3, 4 should be, yeah, that's the thing. Yeah, so this one you need to store in the yeah, so I mean you have an array list to store all linked list. That means you store this thing in this array list. So we were given the linked list and array list, but store your answer. In the end, you just you just store, you just return. Where is my template? I need to recall exactly what I'm doing. I need you to return I pass you is I create a linked list. I create a linked list and array list. So a bit forgot what is I did. When I print in the end, in my main function, you can see that I print the arrays notes. I print the array list. I print the array list. I print the array list. Actually, you array list. What is in the end? Actually, I print the array list. Temp ll when I did the linked list. This linked list is for, wow, forgot when I wrote this thing some time ago. Let me recall the assignment. No, let me find my things. The linked list sum. Okay. Yeah, I think the linked list is just assist you to build the array list. So in the end, you can see my main function. I only need you to return the array list. Yeah. The linked list is just helping you. I think maybe you may not need to use it. You may not. Yeah, depend how you implement. But definitely, you can see in my main function, I only use the array list. I need you to give me the array list to print out the things. That's why I cannot. Yeah. That's why this question I don't want you I don't allow you to use the. Yeah, you have to use the template. You cannot. Yeah, you have to follow because I want you to put your result in the array list. Yeah. Okay. We are given the linked list and array list for stored answer. Yeah, you can see the output print. So this one answer. Linked list is just for the combine. Yes, combine the combination. Yes. So how I didn't receive. Okay, for if you some of you may not receive the email. I guess it's due to the school mailbox server that sometimes they may filter out this kind auto reply email. So they may not send you the notice. They send you the notice, but just school the server somehow they will filter out all these notice. So it's okay, don't worry. If you do submit or you didn't end the test, Saturday midnight already close it. Yeah, they auto end the test already. Whether you end it or non end it, the system will automatically end the test. Yeah, then they already generate the result. I'm just trying to compile the result. I haven't got time to upload it to NTU Learn. Later, maybe, I don't know, maybe I trying by this Saturday, I trying to upload the result to you for the assignment file. Okay? Then the next one, you can store one particular 1, 2, 3 in your linked list transfer. Okay, this one already explained the thing. Okay, I think that is the query about that. Yeah. So the match, I think. Okay, one more question about the last question about the match will cover in the letter. The matching problem we will discuss. Yeah. So I guess what you get, what your question is about. Yeah, that means you got student. It's a bit like you have a project, then you have a few mentor or supervisor. Student can choose the project, also can choose the supervisor. So they need to find the maximum match. That means maybe A like project 1, 2, 3, B like project 3, 4, 5. Yeah, then A like mentor 1, 2, 3, then B like mentor 4, 5, 6. Yeah, what is the maximum match? That means you need to match the student and the project and the student and the mentor. So it's got 3 factors you need to match. Yeah, the project, mentor, and student. Yeah. So that is the match means. Yeah, we will cover this algorithm, I think next week. Yeah, next Monday lecture. Today, the one I want cover related to the assignment question 3 somehow. This is the dynamic programming. Okay, dynamic programming, maybe some of you have heard about it. Okay, it's developed by this person, Richard Ernest Bellman, in 1953. Yeah, I think probably this one, I guess, is like during that times, the computer coming up, semiconductor, people make the transistor, then they start come out the memory. They start able to store something. Yeah, so not surprising that someone trying to able to develop this dynamic programming. But one thing, what is dynamic programming? Actually, it's not programming. This thing is not the coding. Okay, this programming, this word, it's not really a program. Means not a programming. It should refer to planning, to it's a tabular matter. You can think that kind of like filling the table. Yeah, there are a lot of this kind of programming in mathematics, in optimization. In this mathematical optimization area, got linear programming, the integer programming, convex, semi-definite, and so on and so forth. But actually, they are not related to coding itself. Okay, so for dynamic programming, the idea starting is, yeah, like I said, they come from, yeah, when we have some memory, able to remember what just now happens. Yeah, especially in people working, I think this is should be working in control earlier. That's mean they have some process. Yeah, they need to know, like at the state t minus, yeah, you want to know what is the output or what is the state t. Yeah, you need to know what happened in the state t minus 1. Yeah, to know what is the state t minus 1, you need to know what is the state t minus 2. Sometimes maybe you need to know previous few state. Yeah, minus 3 to dot 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 dot. So you need to combine the previous history state, then you can make a decision for the current state. Yeah, so that is like why there's a dynamic coming in. They involve the times. Over the times, the process is keep moving on. But every time you decide your control process, you want to control, you want to adjust your process, yeah, your decision is based on the previous few state. Sometimes maybe not just the previous state, it can be a few state. So it's like when the memory start, the concept start coming out, people come out this dynamic programming. Yeah, then after that, people find that this one not only can apply in control, also can apply in economy, can apply in a lot of computer science problem. Yeah, so that's why it become very one of the I would say is a strategy or is a way to solve the problem. Yeah, it's a kind of a strategy to solve the problem. Yeah, using this kind of tabular method to filling the table to keep track the previous result to predict what is the next state or make a decision for the next step. Yeah, so well, in computer science point of view, yeah, it is very similar to divide and conquer strategy. Basically, trying to breaking the big problem into several sub problem and trying to solve the sub problem recursively. But one of the key thing is dynamic programming, their sub problem may not be independent. Yeah, like sorting, you got sorting problem, like you want to solve a few number. Maybe give number better. I want to do the sorting 1, 7, 8, 3, 2, 6, 1, 6, 2, 5. Yeah, I want to sort this data. I'm trying to divide using the divide and conquer strategy. It's like trying to divide into a few sub problem, and then trying to sort individually, sort all these things. Yeah, so they are basically, you can see that all these sub problems are independent, and you're trying to merge them, you're trying to sort them. Yeah, this is divide and conquer strategy. But in dynamic programming, their problem is, yeah, all the sub problem may be overlapping. They may not be independent. Yeah, very likely they are not independent. Because if they are independent, actually dynamic programming, there's no any advantage to improve the solution, improve your algorithm in terms of time complexity. Yeah, so yeah, usually and then also the dynamic programming is trying to find an optimum solution. They're trying to find an optimum solution, but the problem itself can have multiple optimum solution. Okay, so may just return one of them only. So DP may only return one of them. That means you got other solution having the same optimum value, but they're only able to return one of them to you. Yeah, that is the characteristic of dynamic programming. So one of the very typical example, if you recall what you have learned in the very first lecture, we mentioned the Fibonacci series. Yeah, you trying to calculate the F4, for example, you recursively find the F3 and F2. Then to find recursively to find F3, yeah, the Fibonacci number of, yeah, the third term, then you need to find the second term and the first term. Then you sum it up. Then you get, because Fibonacci is start from 1, 1, 2, 1, 1, 2, 3, then 5, then 8, 13. Yeah, so 13 is come from the sum of 8 plus 5. To know what is 13, to know this term, you need to find out 5 and 8. To know 5, you need to calculate the earlier one. 8 is come from 3 plus 5. 5 is come from 3 plus 2, and so on and so forth. So if you notice, actually this recursive process, in this example, for example, you can see that n equal to I equal to 2. I equal to 2, you calculate 2 times. And it get worse. If you go further, find the F5. Actually you find that you repeatedly calculate F3, F2 several times. So that is what the overlapping. You have some sub problem finding the F2 in this example. Finding the F2 is overlapping. If you're not using dynamic programming, you using the so-called divide and conquer strategy, or just simply use the recursive function to solve the problem. Actually, you repeatedly calculate the F2 2 times. So that is the overlapping part. Then you increase your computational time to repeatedly do the solving the same sub problem again and again. So one thing in the dynamic programming, you need to figure out the overlapping sub problem, and you need to have an optimum substructure so that it can easy for you to combine the problem. Combine the sub problem, the solution to the sub problem into bigger problem to solve the bigger problem. So basically, dynamic programming is not just using the recursion to solve the problem recursively. They also have another element called memoization, so which is store the optimum solution into a table, into a memory, into a cache, so that you can reuse. When you find that, for example, this Fibonacci, I find that F2 already calculated earlier, I can reuse it in some way when I need it. So that will be improve my computational times, because I can save my times to recalculate the F2. So that means soon you will find that you doing that, you also don't need to calculate F3, you just need to calculate once. Once you know F3, you don't have to repeatedly calculate F3. Then you can easily find out what is the F4. Then you can easily find out your F5. You don't need to repeatedly calculate all these sub problem again and again. It's due to this particular concept. They're trying to store the result into some memory, into some table. So whenever you encounter the same sub problem, you can reuse it through the table. That also implied that dynamic programming were trying to use this time and space trade-off. That's means I'm trying to use the memory to store a lot of sub problem result temporarily, and reuse them. Then that improve my time complexity. But at the same time, I will increase my space complexity. So after they sort out the things, the problem can be resolved by just calculate F1 one times, F2 one times, F3 one times. Then when you need F4, I can easily use the F3 and F2 result. Just sum it up, I get the F4. So that improve my computational times. But not surprising, you need to store all the result somewhere temporarily. So for reuse purpose. So but you will find that erase all. So you will find that this thing improve the time complexity. This one, I think I have mentioned in the very first lecture in week 7. The time complexity of this one actually is the function of 1 plus square root 5 over 2. Big theta power to n. So which is 1.618 Okay, you can approximate saying there's big theta. I think not accurate. I should say big O. Yeah, I should say big O. Yeah. So you will improve your algorithm from you will improve your algorithm from 2 power to n to big theta m power to p polynomial. That is the why people like dynamic programming. Yeah, because you improve your time complexity from exponential. Yeah, this is something we don't like. Exponential, the algorithm with exponential time complexity is something we don't like. We reduce to polynomial. At least p is a constant, so maybe you can improve. Sometimes maybe in this case, maybe you can improve to linear lah. So it's p n power to 1. Yeah, sometimes some algorithm you only can manage to go to n square or n cube and so on and so forth. But anyway, it's n power to p polynomial. Then that means the p is in constant. P is some constant number. Yeah, so still manageable compared to exponential. Yeah, so that is the advantage of using the dynamic programming compared to using the brute force, just trying to calculate everything again. You also don't care. Repeat the same sub problem, you also don't care. Using that kind of a naive approach, yeah, always you will get the exponential complexity. Yeah. So there are two ways to implement the dynamic programming algorithm. One way is the top-down approach. Yeah, using your backward track, using kind of like a backtracking. I mean, yeah, which we cover in Monday lecture. I think you want to find the answer for this n. Yeah, then you backward track maybe Sn minus 1, and sometimes you may be more than 1, maybe Sn minus 2 also or more. Yeah, I mean the previous earlier or small sub problem. Yeah, recursively you trying to find the earlier one, and this one are trying to find the earlier one or smaller sub problem. In computer science only they think in smaller sub problem. Yeah, recursively. Yeah, top-down approach. Recursively using the solution to its sub problem, and then every time you find that there's any repeated you're trying to remember the sub problem answer, and then whenever you encounter it again, you can reuse it. You through the table to retrieve the solution instead of do the calculation. So that can save you the computation, your time complexity, improve your time complexity. Another way is bottom-up approach. Bottom-up approach, that means I'm trying to start from the S1, S2, S3, and so on and so forth. Then whenever then trying to remember, slowly build out the problem to a larger problem. Whenever I need to use the smaller sub-problem solution, I can just simply through the table again to reuse it. Yeah. So you this thing you need to sort. One thing is you need to sort out the order, because the order is important. Which one you need to calculate first, you need to figure out first. Yeah. So that is the thing. Someone asking about the Fibonacci. Okay, just share with you. The one conventionally we use the recursive function you probably learn in 1103. The one I show you in the lecture 1 in week 7. That one is in exponential, the complexity. And if you use the iterative way, you can that one you can categorize it. It's a kind of a somehow kind of like a dynamic programming. The iterative version you can achieve in linear times. You still in linear times because you need to calculate. Yeah, and actually that is still not the best one. The best you can search online or somewhere. Yeah, you can find that actually calculate the Fibonacci. The best one probably is in logarithmic time. Yeah, you find that actually you are something. How to say? You calculate F1. In short, I think because they involve something you may not know. I don't want to discuss too much. You calculate F1, F2, yeah, you calculate F4. Actually, it's you can find by combining the earlier one to predict. Yeah, you don't have to calculate the F3. You can jump. I think they can jump a few steps to get the F4. Yeah. I think they have some. You can write in the metric form. I think that probably need to use some linear algebra approach. You can count, but you still need to take logarithmic time. It's not possible achieve it in constant time, I think. Okay. Yeah, even you write the explicit formula, you will find that you still need to use logarithmic times to do the calculation. That probably is the best algorithm for calculating the Fibonacci. Yeah, that one will involve some linear algebra knowledge. Yeah. Okay, here we discuss is the linear one using the dynamic programming. So yeah, so bottom up, that's mean you build from 1 to 4. Yeah. Then top down approach is like from here to here. Yeah. To build up the graph and then backtracking to find out the answer. So that is the top-down approach. Okay, so here I just share with you some example. I think here I'm not going to go too details. You may learn the string algorithm in the next level. So at that stage, I just let you know the longest common subsequence, the longest increasing subsequent, the longest common all these are string compare the string between two strings to find out the longest common substring. All this, they can use DP to solve. And graph algorithm you will learn in the next level, like Bell-Manford algorithm. All this, yes. Then metric multiplication, you can see there's a repeated process during the metric multiplication. So not surprising that using the DP also can improve your metric multiplication. Another one is your assignment, the subset sum. That one is one. Here today I will discuss about the 0-1 KnapSack similar, which is also using the DP. We also can solve the problem. Another one is very well known, traveling salesman problem. That means you got 5. I think the story is from US, got 50 cities. Then they want to visit every city once, every state once, and find the shorter path. And then in the end, you need to go back to the first city you visit. You need to find the shorter path. So this one, you can think there's a sub problem. And then you need to find the shorter path for the 49 city. Then you need to find the shorter path for 48 city. If you can find the shorter path of 47 city, then you can find the shorter path from to the 49. And then, but in the end, you find that this thing, is still kind of like exponential. It's just like you can use the DP to build out the graph to find out the solution. The one I want to introduce you is the KnapSack problem. 0-1. 0-1 means that given n item, you have n item. Then and then each item, I item for example, they have a size, different size, some bigger, some smaller, and different value. Then your task, your problem is you need to try to put this item into a KnapSack, which the capacity is C. So you need to put some of them. You may not be able to put all of them. You maybe can put 1, you maybe can put 2, depend the capacity, depend their size. That means the size, the sum of the size, must be less than the C. That's one of the criteria. The one you select, here I define X. X is the either you select it or you don't select it, 0 or 1. If I select it is 0. If I select it is 1. Okay, so the sum of those selected item must be their size must be less than C, your capacity. So if knapsack is that big. I only can put so many item up to C. Yeah. So, but my objective is trying to maximize the value. So the total value must be maximum. So I'm trying to select the item with higher value. But higher value, maybe the object is very large. Yeah, so I got some constraint. I need to keep the size as small as I can so that I can put more item. But yeah, so this is is a kind of an optimization problem. You need to maximize the value, but you have some constraint. You cannot put everything into the bag. Yeah, so you need to make a decision which is the best, yeah, optimum, can maximize the largest value. Yeah. So yeah, why is 0, 1? That means it's like either you select it or you don't select it. Yeah, that means one item you only can select once. In this, I think this one got a lot of version. So the version I'm discuss is, yeah, you select it or you don't select it. Yeah, there's no duplicate item. That means same item you only can select once. Okay, so that is the problem. And how do we solve this problem? This one. One way, very naive approach is just try, because it's each item either I select it or I don't select it. So either this item I select, then means, yeah, it's 1. If I exclude it, then means 0. So that means every item either have a chance being selected or excluded. So it's 0 and 1, 0 and 1, 0 and 1. So not surprising, the time complexity you're using this approach is exponential. Agree? But if you observe carefully, let's say I got 3 items. For example, I got 3 items. Item 1, item 2, item 3. So of course, if you don't select all of them, yeah, the value is 0. If you select item 3, the value is V3. If you select item 2, you got V2. If you select item 2 and 3, it's V2 plus V3. Then you find that if you select item 1 is V1, you select item 1, item 2, item 3 is V1 plus V2 plus V3. Of course, you need to consider the size. Here I assume the capacity is large enough, so no problem to select 3 of them. So yeah, but you can observe that if you really in that scenario, do you notice that, yeah, something is repeatedly calculated. If when I calculate item 2, item 1, if I select item 1, item 2, item 3, all of them, actually I don't have to recalculate the V2 and V2 plus V3 because earlier I already considered item 2 plus item 3, this combination. Yeah, so you can see if you observe carefully, there are some, of course this is a small example. Yeah, you can observe that something is repeatedly calculated. There are some sub-problems are repeated. Yeah, whenever item 2 is selected, yeah. When item 3 is selected, yeah, you have this 3 definitely got the V3. And then this 2, yeah, there's a result of V2. Yeah, so certain there are some sub-problem. Yeah. So you find all the possible. Of course, this is a brute force approach. You soon you'll find that this one, the time complexity is very expensive. Yeah, it's very high. You need to try out all of them and see which fulfill this criteria. Also, you need to consider that, yeah, they must be less than the capacity. Here I assume the knapsack is large enough, so I can occupy the item 1, item 2, item 3. Sometimes the C is very small, then you probably can eliminate some of them already. Yeah, you're not able to put in, maybe item 3 is very large, then you can eliminate them. Here I assume you have a chance to put all of them. Yeah, so that's means and now I need to consider, worst case scenario, I need to consider all of them. Then the complexity will be 2 power to n. But you soon you will realize, you will play a few rounds, you should realize that actually, yeah, you are trying to calculate this thing few times. V2 plus V3. Yeah, here 1 times, here 1 times. Yeah, V3 actually you calculate many times. Here, 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 here. Okay, this one still, because it's small example, repeated part, V1 plus V2, V1 plus V2. Yeah, you do it 2 times, V1 plus V2. You can see that there are some sub problem actually. Yeah, if you can reuse it, you don't have to keep recalculate them. So how the DP coming in? So the DP, dynamic programming, can coming in by solving the problem. That means if I want to solve this problem by DP, I make a table. So each row represent, I select one item. The item 1, I select item 2. What happen if I select item 2? What happen if I select item 3, item 4 to item n? I got n item. Then I need to consider each column along here. I consider that I have capacity 1, 2, 3, 4, 5, 6 to C. C is the maximum I can have. Sometimes the optimum solution may be you didn't fully utilize the whole knapsack. That means your C maybe is 100. Maybe in the end you just need 80. It's good enough already. It's the maximum already. Because the next item you cannot. All the remaining item is greater than, let's say my C is 100. Yeah, I got n item. It's possible that you only, in the end, you only use 80 instead of 100, because the remaining item all are greater than 20, their size. You have no chance to add in any new item, and this combination give you the maximum value. Yeah, you cannot put in any extra item because the rest of them are more than 20. Their size is more than 20. Yeah, so it's possible that the result, the maximum, come with less than C. The capacity is less than C, but the value is maximum. So I need to build this table, to find out all the scenario. But you can see that actually if I'm doing so, the complexity will be n by C. My computational time is the n times C. Yeah, because it's a metric only. I just fill out the table. Yeah, it's like select item 1. Then so how to fill out this table? Like item 1, you're trying to starting definitely is 0, 0. You only can use item 1 is from their after certain value, the size depend on the size of item 1. If the item 1 the size is 3, that means on 3 onward, okay, no problem. V1, 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 V1. Yeah, that means your capacity is 3 or C is equal to 3 or C equal to 4 or 5. Yeah, all this V1, no problem. That means from here onward you can put item 1. Then item 2, same scenario. Yeah, you're trying to if you want to know item, you put item 1 and item 2. What happened? Yeah, in that circumstance, you maybe item 2 the size is 2. So you can here you only can put 1 item. When your item when your size, your C is equal to 3, then maybe I only can put item 1. Item 2, I have no space. Based on this column. Based on the next column, maybe I have a chance to put V1 and V2 to maximize my value, and so on and so forth. So that means every cells you fill in, you consider this position. Actually, you need to consider is two things. When you are here, somewhere here, okay, the ij, you consider is 2. The current item, whether you want to use it or not use it. Just like this one, in the end, I won't be able to select V2 because I need to consider is whether put V1 have higher value or V2, because I only can select if my C is equal to 3. If my maximum size is equal to 3, I only can put 1 item, either V1 or V2. But after I compare V1 and V2, I find that V1 value is higher, so I decide to put V1. Yeah, similarly, I can fill out this table. When I decide when I in this side, these cells, ij, this position, I need to decide whether I want to, what is the value I want to put, which are the item I can put in this particular location. Yeah, first I need to consider is I minus 1 and yeah, I minus 1. That means I'm trying to including this particular I item. The I item. So I need to think that if I include I item, I need to have sufficient size, sufficient capacity for me to put I item, right? So I need to find that I minus 1, what is the maximum value at I minus 1, j minus the size. So this value plus the current I item. Yeah, this one I need to consider this. Yeah, that means I'm trying to include I item into this knapsack. This is one thing can be the answer. Another thing can be the answer is I don't include the I item. I don't include the I item. That means I just simply find what is the previous value when I item is not included, which is I minus 1. Then of course the size will be the same. The capacity will be the same. So in this position, what is the value? Then compare these two, which one gives me higher value? That will be the value for this particular position. Agree? So it's considered when every time you fill in this table, you consider is like whether you want to include the I item or not. If you include the I item, then the total value is I item value. The I item value, this one, the I item value plus, yeah, I minus 1 and j minus the size. You need to reserve so many size, the capacity for I item. So you need to know what is the value I minus 1, j minus size to decide. Yes. So for each column, you iteratively over the row, yeah, and trying to decide whether you want to keep this item, include this item, or not include this item. And which one give me the highest value? Is include I item or not include I item. So that's why you can see just now, clean up. Previous one. You can see when I'm in this position, when my M is 2, 3. Actually, I need to, 2, 3, right? I need to consider is which one is maximum? Yeah, which is maximum. Either I include the item 2, I include the I item 2, I include the I item, I include the I not include I item first. Okay, the first one is so is I minus 1. So is 1 and j, yeah. This one. And whether this one is higher or the other scenario is 1 and maybe, I don't know here I didn't, yeah, the item 2, the size of item 2, I need to minus the item 2 size. Maybe here, maybe somewhere here, I don't know. Yeah. That is 1, 1, maybe, yeah, plus V2. Yeah. So is V1 larger? Okay, this one not surprising is 0 . So this one is V1 based on here. So is V1 largest or V2 largest? So in the end, let's say V1 is larger. So I will pick at this position. Yeah, I will pick item 1. If your capacity is 3, yeah, item 1 and item 2, in the end, I will select item 1. So I keep doing this iteratively from the in this table, from the top left corner all the way to iteratively calculate it toward the right bottom corner. Then you find out the answer. What do you mean by size? By size. The size, the capacity. There's in every item there's a capacity. There's some book may be called the weight, some book may be called the size. That means definitely you got a limitation. You cannot put everything into the knapsack. So like at this moment, like at the 2-3, this position, you only have your capacity is 3. Your capacity only 3. And then item 1 and item 2, you only can select one of them to put in. Then of course not surprising, you just choose the one give you the largest value lah. Always give you the optimum. I would say that they give you the optimum solution when because what is the best is the thing unclear. Here is optimum because they're looking for largest value. In the end, they're trying to look for the largest value. Well, maybe there are multiple solutions, but they will give you one of the solution. One of the optimum solution. One of the largest combination, the combination which give you the largest value. I think you back to the question actually is okay. This thing actually you need to find what is the maximum. This is your objective. Your objective, you need to find the maximum value. Yeah, by selecting the right combination, can give you the largest value. So through this, this is a kind you can observe is actually I'm bottom up. I'm slowly build out the answer from when the capacity is 1, and then I only trying to select the item 1. Then after that build out, then item 1 and item 2, I trying to make a decision. Yeah, the combination. Then item 1, item 2, item 3. Yeah, then what is the answer? Item 1, 2, 3, 4, 5, 6 to N. And then the capacity is C. Yeah, what is the answer? Maybe I should use red color. So yeah, the capacity is C. And then you have N item. So what is the value? Yeah, so you can see I bottom up, build out this table. Of course, there's another way you can write in the recursive function. It's like you want to know this answer. You want to know that you have N item, and then you have your capacity is C. Yeah, then what is the solution? Is like whether if you excluding the N item, yeah, then what is the maximum value? Yeah, which is excluding, not use, or use including the N item. Yeah, but you're trying to find the corresponding, the minus the size. Yeah, what is the value? Yeah, so basically they were trying to take this value somewhere earlier, somewhere here, likely somewhere at this table, this size, and the other one I minus 1, yeah, which is this one, I minus 1j I minus 1j should be the previous one to make a decision. So if you take ij, I minus size plus size, where the initial m is 2, 3, why does mij j minus is I just trying to give you the example saying that the size 2, if my size 2 is equal to 2 lah, I think the capacity, the size of item 2 is 2. Yeah, so now I'm in, am I right to set 1, just like I said 1, is it? J is equal to, yeah, correct, J equal to 3 3 minus 2 J equal to 3, the size is 2, so yeah, it's 1, 1 yeah. Okay, so this is the bottom-up approach. But well, you also can implement it in the top-down approach. Then you start from the last element, backward check the answer. Yeah, recursively. Does the time complexity this include the insert? Yeah, I'm actually when you calculate it from the, like I said, that if I bottom up, I'm talking bottom up approach, it's like from the top left corner to do the calculation. Yeah, so each element, each position I'm trying to do the calculation actually is constant time. I just need to know this position and this position, which one larger. Yeah, just use this formula. This formula, whether you take this item or not take this item, constant time. I can immediately tell you the answer. Yeah, so in constant time, so what is the time complexity? Then how big this metric is. This 2D array, the size is n. This one, the size, how many column? C. You have C column, you have n item, so the complexity is n times C. Of course, C can be very large, if possible. Yeah, so it can be, yeah, this thing may be not that cheap. The time complexity can be still quite high, because C can be very large number. Yeah, C can be a lot larger than N. Not surprising. Yeah, then you need to consider every cases. Yeah, and C equal to 1, C equal to 2, C equal to 3, C equal to 4, C equal to 5, 6, 7, 8, 9, 10 to the largest number. Yeah, so it can be quite scary. Although it look like linear, but actually not true. The C, I put C doesn't mean constant. Yeah, one thing you need to take note, C is a capacity here. Okay? So, well, just introduce you. Another one is the top-down approach. You will find that this is, sometimes you need to use the backtracking technique to solve this top-down approach. Yeah, so that will be used something similar to Edquin problem, idea to backtrack, or that first search technique to help you to backtracking the answer. Yeah. In practice, I think sometimes you find that this kind of dynamic programming, they not really need to build the table declare a 2D array and then put the table there. Sometimes it's like dynamically they trying to do the calculation. Yeah. But you find that they still store the things, like especially recursive one, they maybe use the stack memory. Because when you recursive call, actually implicitly they build out the stack memory. So that one, maybe you didn't explicitly build the 2D array to store the data, store the result, to memorize all the result. But actually you still apply it implicitly. Okay? Probably this is two backtracking and dynamic programming, which is quite a lot of problem. I think it's quite popular in use. So, well, that is dynamic programming for today's lecture. Next Monday and Wednesday, I will cover the last thing, which is someone just now asking the matching problem for the last question in the assignment. And also, that is one of a special case of maximum flow. Yeah, and like earlier, I told you the things. Discuss. If you have a photo, maybe in fact this photo. Okay. Actually, in the I think I showed you before. Actually, the background, how they remove the background. I think earlier got the background. I already removed it. How they know that the foreground and background. Actually, they are using the maximum flow or minimum cut to find out the edges. This is what the Microsoft developed this particular algorithm for this background remover. So we will discuss next Monday and Wednesday about this maximum flow matching problem. Next week. Okay. Discuss all the changes. Recover. Okay. Any question? Maybe this is like important. Okay. This come from somewhere here. One of the cells at the in its top left corner somewhere. One of them, and or this one. Which one is the maximum based on the given formula? That is how using the DP to solve this 0-1 knapsack problem. Okay. Any question? If no, I will end today's lecture. Thank you. Okay.